question, important question. Can we represent any 2 pi periodic function in the trigonometric series? Yeah. The answer is yes. Yeah. Yes, but under some conditions. Yeah. So you need to make sure the function is good enough. Okay. Yeah. Following some reasonable. Yeah. Because in our real world applications, most of the periodic phenomena we can use reasonably good functions. Yeah. But here, when we talk about 2 pi periodic, here, 2 pi periodic, so you can see this orthogonality property. I take integral from 0 to 2 pi. It covers one period. Okay, covers one period. Yeah. But because it's a periodic function, if you take any period coverage, you take integral, the same. Result is the same because you cover exactly one period. Yeah. Then, so many people, they like to write the period not from 0 to 2 pi. 0 to 2 pi is one way to represent one period for sine cosine. But another commonly used period is this one. From negative pi to pi. Okay? Yeah. And then you have the same thing. Nx dx equals 0. Okay? The only change, you just change your period. Okay? From negative pi to pi. All right? Yeah. So, because one period, you take integral for this period and that period, result is the same. Okay? Yeah. The function values, periodic 2 pi periodic function, you shift, you get the same. All right? Yeah, but here, why this period selection? So this special period selection has its advantage. Yeah. This period, so later you will see most of our formulas, we use this period selection. The period from negative pi to pi. It has advantage. The reason is simple. The reason, so if you look at the coordinate system, pi here, negative pi here, so your period, you cover one period like that, and you can see this period symmetric about y-axis. So here, suppose this is y-axis, this is x. So this period is symmetric about y-axis. Yeah. Because later you will see we will use some functions with symmetric property. Yeah. Symmetric property. Okay? Yeah. Yeah. So when a function has symmetric property, then our Fourier series can be simplified. Our Fourier series can be greatly simplified. Yeah. All right, so we will get there. All right. Euler formulas for Fourier coefficients. This Euler formula different from that famous Euler formula. Okay, so EI, so that famous Euler formula. This about the Fourier series, the Fourier coefficients. Yeah, because Euler discovered many formulas, large number of formulas. Yeah. All right. Suppose that f of x is a given function of period 2 pi, and it is such that, I miss something? Yeah, I may miss something. It can be represented by, yeah. All right. Yeah. Anyway, yeah. So here, because you need to satisfy certain condition. Here, I may like to talk about some, certain condition, but I do not need to write explicitly. All right. Yeah. So that represented by this one. Yeah. Actually, that condition, later you will see. Yeah. continuous, but we allow finite number of discontinuity points. Yeah, I talked about before. Yeah. So if your function has that property, okay? All right. So the function should be continuous except at finitely many points, not continuous. Yes. Okay? Yeah. Finitely many non-continuous points. Yeah. So that's the minimum requirement we need for this function. Then we can represent that function in this trigonometric series. But how to determine these coefficients, right? Little a's, b's, coefficients. Euler formula tells us a0, you take this integral. Because f function is known. Then you take this integral, you can calculate a0. Okay? F function is known, then cosine n, so you can calculate all these coefficients. That's the, Euler formulas. Yeah. But to get these formulas, it's very simple. Yeah? If you use the property of our previous slide, orthogonality, then you can get these formulas quickly. Yeah. Orthogonality, you just take integral with all these different basis functions. Yeah. Individual basis functions. Yeah. When the basis functions are different, you get a 0 because of orthogonality. You get 0, okay? Only one term non-zero. Yeah. That's the one term non-zero, okay? Non-zero. Yeah. Yeah. So you get the coefficients. Yeah. That. Okay. All right. Yeah. So now, with these formulas, later you will see, given f function, we just calculate. We can calculate its Fourier series. Yeah, we call it Fourier series. Yeah. But we need to, later, I need to explain the convergence. Yeah. 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 At least you need to know a little bit about convergence. Yeah. So, I will explain. Yeah. Not very difficult. Yeah. All right. Assume that the trigonometric series is convergent. Yeah. Yeah. So later we have some theorem. Yeah. Some theorem tells you about the convergence. Yeah. Okay. All right. Periodic rectangular wave. So now let's do one simple example. Let us expand one periodic rectangular wave function in its Fourier series. Okay? Yeah, our first Fourier series example. Yeah. Find the Fourier coefficients of the periodic function f of x. F of x defined in this way. Okay? Yeah. All right. So here you can see around y-axis. Yeah. So the interval, the period interval, with the center at 0. Center at 0. Yeah. Yeah. All right. From negative pi to pi. If we draw graph, you see, for one period, graph, okay, negative k, positive k, for one period. Then you repeat that period, okay? Yeah, everywhere. Everywhere. Okay. That's the periodic function. So this periodic function, we want to calculate its Fourier coefficients, Fourier series. Yeah. Yeah. All right. Yeah. First, let's calculate an by the Euler formula. Okay. F of x definition. Yeah. On one period. Yeah. We work on one period. Okay. All right. Then, because the f value at the first half of the period, it takes negative k. Second half, positive k. Yeah. All right. And we can find integral, definite integral easily. All right, so equals 0. See, a0 equal to 0. Cancel out. Negative k, positive k. Actually, even without negative k, positive k, sine n times pi all 0, right? All the sine terms all 0. Okay? So even we do not need to cancel out. When we look at the sine terms, they're already 0. All right. But here, I want to include the a0 here, because when cosine n equals 0, then it's 1. Cosine 0 is 1. So you calculate a0, it's also 0. Excuse me. All right. So now you can see for this special function, all a coefficients, all 0. All a coefficients 0. Later we will see there is some reason why a coefficient all 0. Because there is some symmetry. Look at the symmetry. The graph gives you some symmetry, right? Anti-symmetry. So it's not symmetric, but negative anti-symmetry. Okay? So that caused caused all these a coefficients 0. All right. Then b coefficients non-zero. Okay? B coefficients. When we calculate, because the cosine. Okay? Cosine right. So we get this expression. This expression. But n pi, cosine n pi, you need to consider n even and odd number, right? When n is even number, cosine n pi equals 1, 1 minus 1, 0. So when n is an even number, the cosine, these b coefficients also 0. But when n is an odd number, cosine odd number times pi, negative 1. So 1 minus negative 1. Right? So you can see, all right. Minus 2. All right. Then you can see b coefficients. b1 non-zero because subscript odd number non-zero. b2 subscript even, so it becomes 1, 1 minus 1, 0. Okay? So you can see the b coefficients non-zero. Okay? So finally, we can write Fourier series expansion for f function in this way. Okay? All these sine terms, but sine odd terms, odd times x. See? So this is our first Fourier series. So the question, let us study this example a little bit. There are some interesting properties here. So we need to pay attention. Okay? All right. First, look at the expressions we have here. Sine functions. We know each sine function, very nice, right? The wave curve, very nice. Okay? The sum of all these good and nice sine functions, we use this summation to approximate original periodic function. But original periodic function has many discontinuities, right? At 0, it's discontinuous. At pi, at a multiple of pi, it's discontinuous. Okay? Here, our first observation, we feel a little strange. How can we use a sequence of continuous, very nice continuous function? We add them we take summation and take the limit. Yeah, because infinite series, we need to take limit. After we take the limit, it approximates this function with discontinuities. Yeah, that's something not easy to see, at least, right? Yeah, we expect the good functions, when you approximate, you should have also good function as its limit function, right? Yeah. So here, its limit function is like that. Okay, not very smooth. Okay, so many discontinuities. Okay, yeah. Yeah. So we want to see that question. Does it make sense to use a sequence of continuous functions to approximate a discontinuous function? Yeah. 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 By some people's intuition, they may feel not quite right. Yeah. But actually, because when you take the limit, so here there is a limit process. Okay, the summation dot dot dot, there is a limit process. When we talk about convergence, you need to make sure the limit exists. Convergence. Okay, yeah. So there is a limit process. So the limit function here, I'll give you the result, conclusion here. The limit function of a sequence of function is not necessarily a continuous function. Okay? So, yeah, you have a sequence of continuous function. Okay? So, then you take limit. Yeah, we assume the limit exists. Okay? But that limit function, you cannot require it's continuous. It may not be continuous. Yeah. So that's what we see here. Not continuous. Okay? Yeah. A lot of discontinuities. Okay? All right. Here, I want to show you, because I want to convince you, this answer, this Fourier expansion, Fourier series expansions make sense. Or, if we use the approximation view, it's correct. Yeah, I want to show that point. Yeah. All right. Yeah. To see the approximation, how good is the approximation, we call it partial sum, right? Remember, in the power series, we use the partial sum concept. Here, in this trigonometric series, we also use the partial sum concept. So this is the partial sum concept. We only take, summation up to, nth term. Yeah. The last term, n. Yeah. Yeah. All right. Then, S1, the first partial sum is the simple function. Second partial sum containing two sine terms, and the third partial sum, we just look at these three partial sum functions and look at how good they approximate our destination function. Our destination, it's not a continuous function. But these three continuous functions, how well these three continuous functions approximate our destination function. Okay, yeah. So let's draw a graph. Yeah. The first partial sum, that's a typical sine function. The first partial sum, look at how good is the approximation. Not very good, right? But you can see the shape a little bit, right? Yeah. The down part, upper part, you can see the shape a little bit, okay? Reflect the shape a little bit. Yeah. But the approximation is not very good. But the second partial sum, look at much better, right? Much better approximate our destination function. Okay? Yeah? Yeah? Yeah. But it's a continuous, smooth function. Okay? All right. The third one, you can see the approximation much better. See? Yeah, very close to the destination. Right? But think about, if we do partial sum, we take more and more terms, the approximation should be better and better, right? Finally, at the end, so we feel we have confidence the final limit approaches to this destination function. Yeah, so we have confidence. Okay, yeah, it looks right. Yeah, the approximation. Okay, trigonometric series, the Fourier series expansion. Yeah, the general form, the shape. Yeah. Pretty good. Yeah. All right. Yeah. Then next thing. Understand the discontinuity. Yeah. This time, let us focus on these points with discontinuities. And these discontinuities, what are the values of the Fourier series? Yeah, this is the Fourier series. We can evaluate the values at the discontinuity points, right? Yeah, we plug in. Yeah, so x equals pi, multiple of pi. Yeah, so the partial sum here. So here we assume the limit function of the partial sum s exists, converges. Yeah. Limit function, okay, exists. Yeah, yeah. All right. If it exists, that means we can plug in values. Only when this limit function exists, we can plug in the function value. Yeah. All right. Now here, let us plug in x equals 0 and a pi. Okay. X equals 0. All these sign terms equal 0, right? All terms 0. Add them up. Infinite many 0. Add up. Also 0. Okay. Yeah. So from the Fourier series value, also give us the 0. Okay. All right. But if you look at our original function, do we have the definition as 0 and a pi? No. We don't have definition, right? So k, negative k between minus pi and 0, positive k between 0 and a pi, but nothing at 0, right? What's the value at 0? We don't know. It's not defined. So the original function is not defined at 0. No definition. Yeah. Yeah. But we don't worry about it. If it's not defined, yeah, because in one period, here, when we consider one period, only at one point the function is not defined. That one is finite many, right? Because our condition, we allow finite many points not defined. Yeah. Finite many points not defined. So we can still handle that. Okay. Here, only one point not defined in one period. So we can handle it. All right. But its Fourier series has the value at the 0 point. The Fourier series value, its value is 0. Can you see any special thing? This 0 value, why? So this 0 value is here. Anything special, this 0 value? And look at the k, negative k, these, left-hand side, negative k, right-hand side, positive k, but Fourier series takes 0 value here. Can you see some rule, some property? Observe some property from the graph. 0 is the midpoint of those 2 points. Negative k point, positive k, the midpoint, average of the points from two sides. That's the property. Okay? That's the property. So here we consider left limit, yeah, because this function is discontinuous. At this point, discontinuous. When it is discontinuous, can we look at its left-hand limit? We take limit from the left-hand side. We take left limit, okay, and the right-hand limit from this side, okay? Yeah. So we have 2 limit numbers for this function. They are different, okay? They are different. All right. So now, let's at a discontinuity point, x equals x0. Let's assume this is x0, okay? One x0 point. Then the limit function, if we evaluate at x0, it equals average of that function, its left-hand limit. This is its left-hand limit. Minus 0, that means we take limit from the negative side. Okay? We take limit, we approach this point from negative side. Plus 0, we approach to this point from the right-hand side, positive side. Okay? Yeah. These two numbers, for discontinuity, they are different. They are different. The Fourier series, the limit function, it takes its value at this discontinuity point is the average of these two numbers. Okay? Yeah. So here, this, here I write the right-hand limit in this way. X0 plus 0. What's the meaning of that, right? So you may wonder, yeah, what's the meaning of that? F of x0 plus 0, plus we mean right-hand limit, okay? Yeah. The h approaches 0, here 0 plus. Plus tells you from the positive direction, okay? Do not go to the negative direction. Plus means you go from positive direction. H is a positive number, okay? But it approaches 0. That's the right-hand limit. Yeah. Similarly, we define left-hand limit. Yeah. Yeah. So then the Fourier series convergent. The Fourier series is convergent at this discontinuity point, converges to this number. Okay? This is the number it converges. Okay? Yeah. So that is to help you understand the Fourier series behavior at the discontinuity points. Okay? Yeah. Finite many. We have finite many those discontinuity points. Each one, the Fourier series value is that. Yeah. All right. That's one. Another interesting thing. Okay? Yeah. Other than this property, the nice property, another interesting property. Yeah. Look at the Fourier series. Because it approximates at other points. Yeah. So we just talk about the Fourier series, the value at a discontinuity point, right? How about at a continuous point? Then continuous point, same. Okay. Continuous point means the Fourier series, if you evaluate you plug in the number at a continuous point equals the value you plug in into the original function. Okay? Continuous point. Yeah. Same. You plug in. Yeah. It's the same. All right. So now we plug in, consider pi over 2. We plug in pi over 2. Okay? The pi over 2, we know the original function is continuous at pi over 2, right? Yeah. And based on the definition of original function at pi over 2, it's k. Its value is k. Okay? But based on our Fourier series expansion, when x equals pi over 2, sine is 1, all right? Sine 3x, 3 pi over 2, negative 1, right? So you have negative sign, negative 1. 5 pi over 2, positive 1, right? So you see the alternative sign. So this alternative series. Plus, minus, okay? That summation of that series, what's that number? Okay? But this equality is correct based on the Fourier series. Convergent at a continuous point. This is a continuous point. Okay? So it's convergent the same value as the continuous function value, original continuous function value. Okay? That is correct. Can we cancel out that k? K non-zero, right? K non-zero, after we cancel out, can we get what is the pi representation? Can we get a pi representation? So that's interesting, right? Yeah. So after we cancel out that k, we can write pi over 4 equals this alternative series. How about that? How to see that? How can you see that? If someone asks you to prove, it's not easy, right? Yeah, it's not easy. Yeah. You need to make a lot of effort. Make a lot of effort. Yeah. How can you prove this? Pi over 4. Okay? Yeah. But by the Fourier series expansion of that simple function, we get a proof. We can use this as the proof. Can you see that? We can use this result as the proof. How about that? How about that? Is that interesting? Yeah. For mathematician, yeah, at least the first time, one mathematician, if that mathematician saw this sequence, equals pi over 2, then he should feel very excited. Yeah. Because we know the pi number, it's very irregular, right? Yeah. There is no pattern you can find in pi digits after the decimal point. Yeah, but here, it looks like, these numbers follow some pattern, nice pattern. See? Yeah? Yeah. All right? Yeah. 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 All right. So this example tells us, using the Fourier, we can call it, what's that? Side product, right? Some side product, because we do not try to prove, we do not try to derive pi expression, right? Yeah, when we do calculation, we never thought about, we want to represent pi in some certain way. It's a side product. Okay? Yeah? Yeah. Yeah. And using Fourier series, you can get many formulas like this. Yeah? Many formulas like that. Like this. Okay? Yeah? You just use different f functions, you do Fourier series expansion. Then you can get different formulas. Yeah. So this phenomenon, this phenomenon, so you can think about. Yeah. So at least we summarize in problem solving. Sometimes some problem is solved by side product. Okay, you're not targeting on that particular problem. So you're targeting on one specific problem, but by accident, you solve another problem. That could happen in problem solving, like this one. Okay? Yeah. Yeah. All right. Yeah. Yeah. So let's look at a few more examples. 8.2. Fourier series for periodic functions with arbitrary period. Yeah. Why you always use 2 pi as the period? We know sine cosine function, they have 2 pi period. But in the real world applications, it's not necessary you always have 2 pi. Actually, it's rare to have 2 pi period, right? The real world, rotation, so you have rotating parts. In general, the period should not be 2 pi, right? In general, the period, not 2 pi. Okay? The frequency, the frequency and the period, right? So we should consider the period not 2 pi. So here, let's consider 2L period. 2L, okay? The L could be any positive number. Then we can handle all the periodic functions. Okay? Yeah. But you may ask me, why 2, right? Why not 1L? Why 2L? Yeah. Yeah. The good reason is you can draw the period in a symmetric way. Okay? Yeah. the midpoint, the center is at 0, then left-hand side you have 1/2 L, half of the period. Right-hand side you have another half of the period. Okay, left L, right L, symmetric. Okay, yeah. So for convenience, yeah. So you can say because reason for convenience. Okay, yeah. All right. Now, yeah. Let me just derive the formula for arbitrary period L. Yeah. So we finish today's content. Yeah. Question. We have the results for 2 pi period already. Now we want to use our existing result. We don't want to start from scratch. Okay? Yeah. So we just do some connection. Yeah. Can we convert 2L periodic function to a 2 pi periodic function? Yeah. They should be correlated. Okay? Yeah. Yeah. If we can find the correlationship between these two cases, then we can use the existing formulas. Yeah. All right? Yeah. So that's simple. Yeah. All right. Idea, change the period by scaling the variable. Yeah. We can change the period. Actually, we did once before. Remember, in our one of the questions, omega, remember our, spring, mass spring system, omega, how do we calculate the pi? We take one factor out, right? Omega, yeah. So we did something before. Here we use the same way to do it. All right. When we start, assume f function its original period 2L. Yeah. When we start, we have a 2L periodic function. Now we want to change the variable to get a 2 pi periodic function, so we can apply existing formulas. We have all the formulas for 2 pi periodic functions, so we use those formulas. Then we change back to the L periodic version. All right, question. How to define another periodic function with the same value? Yeah. We should keep the same value. We don't want to change the function value, right? Yeah. So we don't want to change the function. Yeah. Yeah. But we can change the variable, right? Variable substitution. Yeah. We frequently use variable substitution. Yeah. Here we just use another appropriate variable substitution to change the variable. Okay? Yeah. With a different period. Yeah. So here, let x equals s times v. S means for the scale. Yeah. Because we need to determine appropriate scale. We scale it. Okay? V is the variable. Yeah. X equals a constant s. S is a constant to be determined. S some constant scale to be determined. Yeah. V is the variable. Okay? Another new variable. So we need to determine appropriate s to make, the new function has the 2 pi period. Then we can apply 2 pi periodic function formulas. All right. Let's replace x by sv. So we have that same formula. Okay. Now, in order to see the new period, now I ask you, what's the new period of this function f using the v variable? This time, f function uses v as the variable. Okay, new variable. New variable means the period also new. Okay, you cannot use the old period. The period it must be different. Okay, all right. So let's write s of sv in this side. We can factor s. S is a constant. We factor s out. Inside the parenthesis, we have v plus 2L over s. Look at this function. Left-hand side, f of sv, you just look at the variable part. Yeah, because if you compare the definition of period, you basically you look at the variable side, right? You only look at the variable part. You ignore other non-variable part. Okay? So here you focus on the variable part. Left hand side of V, right hand side of V plus 2L over S. Based on the definition of period, is this the new period? Your V plus a constant, you get the same function, original function, same value as the original function. That means this is a period, okay? Based on the period definition. Yeah. And we want to make this period equal 2 pi, right? Yeah. Because our goal, we want to get a 2 pi periodic function. So we force this period representation to be 2 pi, so we can find this S. S equals L over pi. S equals L over pi, okay? Yeah. So we determine that appropriate S, scale, the scale number S, okay? Yeah. Let's plug in back to the original function f of x. Now this time we replace x by L over pi times V, yeah? Because this version, this V version, has 2 pi period. The period, 2 pi, okay? If its period is 2 pi, then we can write its Fourier series using the 2 pi version. 2 pi formula, how about that? 2 pi formula, okay? Yeah? So we have the 2 pi formula, existing formula, yeah? So A0, yeah, because here we use the 2 pi version, okay? All right, yeah. But this A0 2 pi version, we want to convert it to period L, 2L version. Yeah. 2 pi version because that's the intermediate formula. So our goal, we want to get the 2L version formula. Yeah. That's more convenient to use. Yeah. To do that, let x equal L over pi times V. Yeah, we do this. We let x to be that. All right. So this integral f of x and the V, you use this V. So V equals pi over L times x. dV equals pi over L times dx. Okay, dx. All right. Yeah. So then you can do the variable substitution. Your integral limit this time from negative L to L, and you have the new integral expression on the 2L interval this time. Yeah? So look at this 2L version of the integral. Okay? All right. Similarly, the variable substitution, also in this AN formula, we do variable substitution. Yeah. So we get a corresponding 2L period version formula. Yeah. They're pretty straightforward. Yeah. We don't need to do too much work. Okay? Yeah. All right. And the B coefficient, we also have its 2L period version formula. Okay? Yeah? Yeah. Yeah. So here you can see, yeah, in this way. Yeah. So, yeah, we can give an arbitrary period, the periodic function with arbitrary period. No problem. We just apply the, these versions of Fourier coefficient formulas. Yeah. Euler formulas. Yeah. Fourier coefficients. So we can calculate Fourier series expansion. Okay? Yeah. All right. So the next slide just summary. Okay? I just list all the formulas. Yeah. So Later, when you have a function with 2L periodic, you just apply these formulas directly. Okay, so you skip the intermediate development work. You just go here and take integrals like because in general in our real world questions, usually we have 2L period, arbitrary 2L period, not 2 pi. Okay? It's rare to get 2 pi period. Okay, so you need to use these formulas to calculate Fourier series. All right, that's it. So let's move to the recovery session number